Yeah, welcome everyone to a new edition of the virtual seminar on geometry with symmetries. And today is my honor to introduce Thibaut Delcroix. I hope I didn't butcher your name too much. Sorry. From the University of Montpellier, and he'll be talking to us about the Yau-Tian-Donaldson conjecture for cohomogeneity-one manifolds. Thanks, Thibaut.
Thanks a lot for the introduction and for the invitation. So indeed, I will be talking about this subject, and that the title is sort of the content of the theorem I want to present. So it says that the Yau-Tian-Donaldson conjecture, or YTD conjecture, is true for polarized cohomogeneity-one manifolds. So I'll say more about I'll say hopefully what's needed to understand the statement, and particular in the first part of the talk I'll explain what the YTD conjecture is, and then the idea, I mean, the idea of the YTD conjecture is to make a link between a differential geometric notion, which is the existence of canonical Kähler metrics on a complex manifold, and in the setting of the talk would be constant scalar curvature Kähler metrics, to a stability notion in algebro-geometric meaning, which is inspired by GIT and the Kobayashi-Chen correspondence for stable vector bundles and Hermite-Einstein metrics, but somewhat different. Yeah, so that's the content of the YTD conjecture, but what I'm more interested in this conjecture is this direction, meaning my motivation is to prove the existence of constant scalar curvature Kähler metrics on some manifolds, and I want to use K-stability to get such existence results. So I'll spend quite a good part of the talk on this problem, and then the other term here that you may know more about is the cohomogeneity-one manifold part. So I can recall a definition and maybe say what I mean by polarized. Let's go back to this also in a minute. I consider projective complex manifold, which is sort of contained in the polarized manifold part, and consider this to be equipped with a holomorphic action of a compact Lie group such that there's at least a codimension-one, a real codimension-one orbit. And actually in the projective complex world, these manifold actually belong to a class of variety which is much more studied from the algebro-geometric side, which is the class of spherical varieties. So I'll say I'll introduce these a bit later on, and then I'll give some ideas of the proof.
Can I interrupt for a second?
Sure.
So when you say polarized, do you think that you're fixing and embedding into projective space? Is that the correct?
Yeah. So maybe I'll go back to this just in a minute. and if that's not clear, then you may interrupt me again. Okay, so I'll start right now, and I'll recall this. But before that, I must sort of apologize, because the work I'm presenting today, even though the motivation is from differential geometric side, my work on this subject is really on the algebro-geometric side. But if you're, it will have implications to existence of CSCK metrics. So it's sort of a motivation to study algebraic geometry if you're not into this in general. Okay, so let me go back to the basics and start with what's the problem, the main problem I'm interested in. So in general, the problem makes sense just if I start from a compact complex manifold and I'm given a Kähler class, which means what? It's some theorem cohomology, the second cohomology group, which contains a Kähler form. And a Kähler form is given, a definition can be given in the following way. It means that omega can be written locally as IDD bar of a function phi, which means I can decompose it write the coefficients with respect to a given holomorphic chart, local holomorphic chart in that way. So the expression, it involves complex data, but in the end, it's really a real two form. And so that's just one way to define a two form, which writes in a particular way, but the Kähler assumption implies, includes as well the assumption that this Hermitian matrix is positive definite at all points. Okay. That's a Kähler form, but it also corresponds to a Kähler metric, which is a Riemannian metric with a good behavior with respect to the complex structure, which is given by the following. Instead of taking the two form, you plug in the complex structure in one of the entries of the two form, and you get then a two tensor, which gives a Riemannian metric. Okay. Then the problem, I'll give a way to get Kähler classes and at the same time say what polarized mean. But before that, the problem I'm interested in, the motivation is, does there exist, given this data of X in a Kähler class, does there exist a Kähler form in alpha with constant scalar curvature? And then I have not defined the scalar curvature, so scalar curvature, maybe an intermediate thing is the Ricci curvature, which which is a two form. The Ricci form corresponds to the Ricci curvature of the Riemannian metric there. It's can be defined locally just in order to be to give definitions. I do it quickly, but the precise expression will not matter much. It can be defined locally if omega is given locally by this function phi by IDD bar of the function defined in terms of phi by this expression. I take the log minus the log of the determinant of this matrix here, which is a Hermitian positive definite, so that gives me a real valued function there. But that's the Ricci curvature, and the scalar curvature is the trace of this with respect to omega, so up to a constant. That's maybe written that way in the Kähler world. I'm taking a quotient of top forms, and this one is a volume form, so this operation is allowed, and it gives me a function from x to r. So a function is constant if it's constant. Okay, so now back to, so I was about to give examples of Kähler classes. So how do you get Kähler classes? Simple way to get these is if, I mean, the simple example, basic example is the projective space, the complex projective space, but I mean, not write the C later on. The complex projective space is a compact complex manifold, and the Fubini's 2D metric corresponds to a Kähler form by this correspondence, which is given by a local function if you take the standard affine charts, it's given by IDD bar of function log of 1 plus the sum of the coordinates, the holomorphic coordinates. This matrix turns out to be CSCK, and even better, it's Kähler-Einstein. And then in general, if you have X, which is a compact complex manifold, to define by embedding it into Pn, then you can take like as Kähler class the Kähler class defined by the restriction of the Fubini's 2D metric to X. This is an example of a Kähler class. And then what I mean by a polarized manifold is that this situation actually corresponds to almost, to a multiple, giving yourself an ample line bundle on X by Kodaya embedding theorem. And then the first Chen class of L is a Kähler class. So in the problem, the previous problem here makes sense whatever the Kähler classes, but for the results I will mention, most of the time I will restrict to the algebraic situation where the Kähler class is coming from an ample line bundle. That's the polarized in the statement. Okay. So this is yeah.
Sorry, yeah. So here ample means that some power, we take sections of some power of this bundle, then they are sufficiently independent so that they give you an embedded into projective space, right?
Yeah, exactly.
Or
so
something like that.
Yeah, so there's two definitions for ample. One is saying that C1 of L is a Kähler class, and that would be
the shortcut. Yeah.
Yeah, and then the other one is just what you said, that
Okay.
if you take the dual to the section of some large power of L, yeah, then you can embed X into this projective space.
An explicit realization of X inside some projective space.
Yes, yes. And then there's the correspondence really with what's above, because the line bundle L is, then if this is I, is the pullback of the O1 on this project.
Tautological.
Tautological, yeah.
Yes.
Or yeah. So you really have this correspondence. If omega Fubini studi is a metric in the Fuchsian class of this line bundle, then this is really the restriction, the class of the restriction. Okay. So now in the YTD conjecture, there are two sides. There's the algebro-geometric side, which is the case stability aspect. So this is it is somewhat heavy for definition, so I will not give the precise definition. I will try to give an idea of what's involved for at least one of the two ingredients of case stability. So we start again from the same data as before, but now I assume that my Kähler class is coming from an ample line bundle, just to simplify, but it's not very important because it's been extended to arbitrary Kähler classes by a while ago, actually, by Darvan and Ross, or just from the other side. So it's not really a strong assumption to say that it comes from a line bundle. There will not be really differences, but yeah, let's consider this. Then to this data, you can associate so-called test configurations, which are the following. So you take the test configuration will be a pair, and the important part is the first, curly X. Curly X is this space here. It would have a projection, a map to C, map pi, such that the fiber over 1 is actually the manifold you started with, X. And you have a C star action on the manifold curly X, but which lifts the standard C star action on C by multiplication. So everything is equivariant. So that means that actually all fibers over non-zero complex number will be isomorphic under this action. And then there's one special fiber which is above 0, which is equipped with an action of C star. This C star action lifts to an action of X0. So this is the picture for curly X, and it is equipped with a relatively ample line bundle L. Relatively meaning essentially that you have this ampleness condition, but for curly L restricted to each fiber. And yeah, I mean, let me take this assumption out, that the fiber of a 1 equipped with the restriction of the line bundle L, this should be isomorphic to X. And if all you started with the line bundle L, but there's a subtlety that you should allow a tensor product. Oh. Well, I'm not writing the full definition, but that's the picture to keep in mind. And then I can give an example as well.
So this is to finite dimensional GIT, what one parameter subgroup would do if you act on your vector, say.
Yeah, yes. So actually,
like a C star action is one parameter sub.
So yeah. So actually, how do you produce these? So you take X to be embedded in Pn by a Kodaira embedding, for example, and then you choose a C star action on Pn, and then you move around the X inside Pn by this C star action, and so you take this set in Pn, and then you take the sort of the closure. But it's, I mean, of course, it's in algebraic geometry, so it should be, I mean, it's actually flat. Yeah, I don't know how to say. No, it's not the closure actually, but take the flat limit of this thing, and it adds. So if you take just the t times x like this, you get the family of a C star. So this should be in a C times Pn. Here, if you take just these, you have the family, the trivial family of a C star, and then you take the flat limit that adds the x0 thing. And that, I mean, that's the one parameter subgroup is really this one parameter subgroup in the automorphism group of Pn. Then you have to consider all possible Pns, and the invariant will be different. But yeah, that's really there's an analogy with the GIT there. And so using this ID, for example, you can get some representative examples of test configurations. the examples that I like to keep in mind are the degeneration of the quadric, the complex world, to a cone over a quadric. So for example, so I can draw the picture in the real plane. That's if I complexify it. So that's a hyperbola. Then that corresponds to a P1 in P2. And I can like vary the parameters inside the equation of a hyperbola and have it degenerate to the corresponding two intersecting lines, which corresponds really to two intersecting P1s. And if you take this family correctly, then you really get an example of a test configuration where X1 is P1 and the central fiber is this thing with two irreducible components. So that's one thing you can have. X0 can have several irreducible components. And so that's the example of a one-dimensional quadric degenerating to a cone over a two-dimensional, zero-dimensional quadric, so 2 points. And if you take the same ID, but in dimension 2, you get a quadric like this, which in dimension 2 case corresponds to P1 times P1. And again, you can have this degenerate to a cone, which is the cone over here, just a circle in the real world. And that's in the complex world, a weighted projective space P112. So this is my X0. And that shows that X0 can acquire singularities, not only from having several irreducible components. And yeah, I'm insisting on X0 because what's important in this data is really X0 equipped with the inducer action of C star and the restriction of the line boundary. So that's the first component of case stability, and the second component is that to each test configuration, you associate a number. So if you think about like the Kobayashi-Hitchin correspondence, this stability of vector bundles, the test configurations correspond to subvector bundles or subsheaves, and the number is the slope. But yeah, the definition is quite more complicated than the slope, so I will not give it at least right now. Maybe if I have the time later, but I think I won't. That's a number called the Donaldson-Futaki invariant. And then if I just allow myself to use these without having given the precise definition, I can now give the definition of case stability. So the pair I started with is called case stable if Donaldson-Futaki invariant of this configuration is positive, is always positive, non-negative, with equality if and only if the central fiber is actually remains isomorphic to X. So the family is globally trivial, and all the fibers are the same. So there are problems with this notion, at least if you want to use it to prove the existence of CSCK metrics. So the first problem would be that the YTD conjecture is not proved in full generality. But the other problem would be that there are too many test configurations. And here, too many means it's a really infinite dimensional space. So really you have an infinite dimensional space of conditions. And for all these, you should be able to compute the Donaldson-Fataki invariant and check its sign. So it's a sort of a unreasonable thing to do in general if you don't have more information. Okay. So, but for the second objection here, I'm writing it's not known in general, but it's known in some cases. The first thing is the direction, which I'm not really interested in today, at least, but which is meaningful as well. The direction from existence of CSCK to K stability. This is known in general. The last step was given by Darman-Darvaslu. But there are positive results also in the other direction. The most important one probably being if L is the anticanonical line bundle, so that means I'm considering Fano manifolds. Then it was one of the major results in the recent years in Kähler geometry by Chen-Donaldson-Sun and Tian, that this is the case stable if and only if there exists a Kähler-Reinstein metric on X, but this is quite easily seen to be equivalent to the existence of a CSCK metric in the Prussian class of this line bundle. So in that situation, the full correspondence is known, and it was one of the big results almost 10 years ago. But even earlier, there were some interesting results in the case of manifolds with symmetries. First one would be when X is a toric surface. Then it was shown by the YTD conjecture, as I stated it, was proved by Donaldson. in 2009. But there is a strong assumption on dimension in addition to the symmetry, which is really, we consider only complex dimension 2 manifolds here. And another interesting result was obtained by 4 authors: Apostolov, Calder-Bank, Cauduchon, and Thomas and Friedman. In the situation where X is the so-called an admissible P1 bundle, then they show that there exists an extremal kilometric, which is a slight generalization of CSCK metrics, if and only if it's uniformly k-stable, say. So here, uniform k-stability, it's a refinement of k-stability. It was actually shown to be necessary, at least for extremal kilometrics, precisely by these authors in that paper. And the YTD conjecture, as I stated, it cannot be true in full generality. You have to consider something stronger in general. But I mean, of course, I'm not writing all possible partial results in the direction of the YTD conjecture here. I'm choosing these 3 for a particular reason, which is the following. In all the 3 results, it is actually enough to consider these configurations with a special property. With x0, such that the x0 has at most 2 irreducible components. So that means that my my second objection to k-stability, in that case, it's almost I mean, it's not so important, in particular in the 2 last cases. And the space of test configurations really becomes a finite dimensional space. So it becomes a reasonable condition to check, and it can actually be checked in practice to say if a toric surface emits a CSCK metric or not, or if an admissible P1 bundle emits an extremal kilometric or not. And I can be a little bit more precise about my theorem B now that I've introduced k-stability. And I can say that if XL is a cohomogeneity-one polarized manifold, then there exists a CSCK metric if and only if XL is k-stable with respect to test configurations with x0 irreducible, so at most 1 irreducible component, and this condition translates into a single simple combinatorial condition. Okay. So I will now say a few words about spherical varieties, and then say a few words about the proof of theorem B. So in my case, so of course there's a quite large group action. In Donaldson's case, there's a large torus action. And in that case, you also have a group action involved, which is not that big, but in the admissible condition, you do quite strong assumptions. For example, assumptions on the base of the bundle. The base should already be CSCK. And then you have this additional C-star action on the fibers, which means that you're really considering a quite symmetric situation, actually. So how do symmetries come into play in my setting, which is purely on the K-stability side? It's through the spherical variety. So I consider X to be a complex manifold. I could consider singular varieties. I even should give the correct definition, but let's stick to smooth for now. So I consider a complex manifold with an action of a connected complex reductive group. And I write it that way to show that one way to think about this is just think about a compactly group and its complexification. Or otherwise, you can think about the classical example of reductive group, which is the general linear group of a C. Then this data is called spherical if a Borel subgroup B of this group KC acts with an open dense orbit in X. For example, in the case of GLN, the upper triangular matrices, that gives you an example of a Borel subgroup. That's a not very enlightening condition, but it turns out to be a definition that works well for several reasons. The first one being that it contains lots of examples, and in particular, it recovers the case of toric manifolds. This is when K is a torus, and then B is equal to KC actually in that case. Toric manifolds are examples of spherical manifolds, and then you also have these projective cohomogeneity-one manifolds, and actually it's not obvious from the two definitions, and the only proof that I know It's actually not really a proof. It's rather that it follows from the classification of cohomogeneity-one manifolds that they are all spherical. I mean, the projective assumption here is important. If you don't add the projective, you get cohomogeneity-one manifolds which are not spherical, where it doesn't even make sense because we are not considering the compact group action does not complexify. Okay. Yeah, so you can get examples. Let me go quickly because my time is running fast. Okay, so how to produce examples of spherical varieties? An easy way to do it is let me put it here. If I consider, I mean, it should have been before this example, if I consider projective homogeneous manifolds, then these are spherical. It follows from the Breuer decomposition in that case. And then how can I produce other examples of spherical manifolds? I can start with a projective homogeneous manifold, for example, Pn, and consider a slightly smaller subgroup. So instead of considering PGL3 here, I consider the subgroup SL2C, which is SU2 complexified. Then that gives me a cohomogeneity-one action on P2. Of course, it's not the most interesting manifold because it's homogeneous, and for the problems I'm considering, these are not very interesting. But if I blow up a fixed point under this action, then I get the blow up of P2 at one point, which is now an interesting cohomogeneity-one manifold. It's a first Hilbert surface. And another example of such a construction is to take the 8-dimensional projective space, but considering as the projectivization of 3x3 matrices. Then on this space, I have an action of SU3 times SU3 complexified or not by left and right multiplications. So again, this is turns out to be a spherical action and actually a cohomogeneity-one action. And again, this may not look interesting, but what I can do is blow up the rank 1 matrices in P8, and that gives me an interesting example of a cohomogeneity-one manifold, which is not a P1 bundle. This one was a P1 bundle over P1. This one is not. Okay. But the upshot for spherical varieties is that like toric manifolds, spherical manifolds are classified and understood using combinatorial data. Okay, so that leads me to the idea of the proof. a few details on the main theorem. So theorem B relies on 3 ingredients. The first is I mean, it is a very interesting thing, but not really my work. But it's ultimately a simple remark of Odaka in an appendix to one of my preprints, which is based on work by Scheele, which provides almost a solution to the YTD conjecture. And in turn, this work is based on, I mean, it uses in an essential way a rather recent breakthrough by Chen and Sheng on the CSCK problem. So this is fully in the differential geometric analysis part. And this gives the passage to algebraic geometry, and then there's an additional ingredient by Odaka, which shows that for spherical manifolds, the existence of a CSCK is equivalent to some notion of K-stability, but which is stronger than the one we want, and which is uniform K-stability. And the second ingredient, which would be my theorem A, which I state in a very informal way, it's a combinatorial. So using this point of view in spherical varieties, it's a combinatorial translation of uniform K-stability for spherical varieties. And then there's a last step needed, which is you have this correspondence, then you have a combinatorial translation of this, but what you would like to have is K-stability implies the existence of CSCK plus a simple condition for K-stability. And that relies on a rather simple, I mean, in the rank 1 case, optimization problem. Okay. So let me say a few words about part 2. So part 2 generalizes a work of Donaldson on the toric situation. So what's the idea? Let me just write it in the toric case. If you have a projective toric variety corresponds to a moment polytope. Okay, which is say integral if I start from a line bundle there, number line bundle. Then what Donaldson proves is that it has configuration for XL. And on this side of the story, it corresponds to a function on the polytope, which is a convex piecewise linear rational, which means that it behaves well with respect to the integral structure function. And that correspondence is quite visual. I mean, thing is, you start from the moment polytope of toric, the initial data, then you want to say something about the test configuration. But if you recall, test configuration, it was something like this. It was equipped with an additional action of C star, but here you start with toric, so your X is equipped with an action of T. So actually, it is enough to consider only a T equivariant test configuration. So that means that you will have an action of a higher dimensional torus on curly X. And actually, it makes it toric as well. So you can consider the moment polytope. So it's not really compact. So it's not really a moment polytope, but almost. And you can try to see what it looks like. And it turns out, as Donaldson observed, that the polytope of the test configuration is given by something like this. You take the cylinder over the polytope of the initial data, and you cut it out by the graph of f, which is a convex piecewise linear function defined on the polytope. Okay, and the number of linearity domains of this function, these correspond to the number of irreducible components in X0. So of course, I didn't say a lot, but you can see that the pieces hopefully gluing together. You have this number of irreducible components, which is easily seen in the combinatorial picture. Then you can also compute the Donaldson-Futaki invariant. It turns out to be quite easy to express on the moment polytope. Should put a constant here, it doesn't matter. But it looks like this. It's like an integral of the function f on the boundary of the polytope minus an integral of the function f over the interior of the polytope. And then just very quickly for the maybe 2 minutes remaining, the ID for 3 is what? I mean, saying things that are not really meaningful is to consider the infimum of all possible values of the Donaldson-Futaki invariant. Then by some compactness result, which is not exactly saying this, it is actually given by a function. I mean, the value of this functional at a function where f infinity is a convex function on the polytope, but not piecewise linear a priori. And the full problem of the third point is to show that f infinity can actually be taken to be piecewise linear. And just the last word, cohomogeneity-one case, dimension of the moment polytope is 1. And so contrast is to write the picture proof of this, even though there are holes. you're considering a minimizer which looks like this, turns out that you can actually just look at this other function and it's also a minimizer. And that gives you a linear function, so a test configuration with an irreducible component. And I will stop here. Thanks for your attention.
Yeah, thanks, Thibaut, for the talk. Are there any questions for the speaker? I do have one quick question. I mean, do you expect this to be possible to generalize to the spherical case, or would that be out of reach still?
Yeah, so what I was hoping for a while was to, so here it's spherical, I mean, cohomogeneity-one is spherical case, but with the moment polytope of dimension 1.
Yeah.
So what I was hoping is that it would be possible to do within dimension 2, meaning to get that you can assume that there's a finite number of irreducible components, and then
right. That would be the next step then.
Yeah, that would be the next step, but it's harder than I thought.
Yeah, no, I sometimes going from 1 to 2. I mean, maybe sometimes going to the general spherical case is not that much harder.
Yeah.
Specific problem, but I know the difference here. In the Riemannian case, there's a huge difference between cohomogeneity-one and higher cohomogeneity.
Yeah, I mean, there's hope because Donaldson's result is for toric suffices, so it's an example of a cohomogeneity-2 thing.
Yeah.
But still, it's harder in the spherical case. Yeah.
Any other questions for Thibaut? Well, if it's not the case, then let's thank him again. Yeah, many thanks. I will stop the recording now.